In this video, we're going to explore quantum chemistry, also touching on SPDF notation, the system chemists use to describe where electrons actually live inside atoms. To understand why this notation even exists, we need to look at how our picture of the atom evolved. The dominant model was Bohr's atom. In that picture, electrons orbited the nucleus the way planets orbit the sun. Every electron lived on a single, perfectly circular track called a shell, each shell representing a specific energy level. It was simple, it was elegant, and it was wrong. The downfall of the Bohr model came from a deceptively simple experimental technique called atomic spectroscopy, the study of the light absorbed or emitted by atoms where electrons change energy states. When an electron drops from a higher energy level to a lower one, it releases light and that light shows up as a line in an emission spectrum. According to Bohr, the hydrogen atom should produce a very clean spectrum with only one electron in a perfectly circular orbit. Each transition should correspond to a single crisp line. But when scientists examined hydrogen with better instruments, they found something completely different. Instead of one line per transition, they saw clusters of closely spaced lines, a fine structure that simple circular orbits couldn't explain, and thus Bohr's model was proven to be wrong. So back to the slide on Bohr's model, this shows that this wasn't a small mistake, and it was a sign that electrons were not following planetary orbits at all, and something deeper was happening inside atoms. The solution came from Erwin Schrödinger, who proposed the radical idea: electrons behave like waves. Rather than tracing out neat paths, electrons exist as spread out wave patterns and their positions can only be described in terms of probability. This led to the Schrödinger model of the atom, our modern quantum picture, and it introduced several key concepts that finally matched experimental reality. The Schrödinger model predicts electrons not as tiny spheres racing around the nucleus in orbits. Instead, they are wave-like objects exhibiting wave-particle duality, and their behavior is governed by a mathematical expression called the Schrödinger equation. Solving this equation gives us wave functions, and when we square those wave functions, we get probability densities, maps showing where an electron is most likely to be found. These probability regions are what we call atomic orbitals. Your sp, d and f orbitals are these. Orbitals aren't orbits like those of the Bohr model of the atom. They don't have sharp edges, instead are fuzzy, three-dimensional shapes that emerge from the mathematics of waves. So, on to SPDF orbitals. Each letter, sp, d and f, correspond to a different type of orbital, each with its own shape and energy characteristics. S orbitals are spherical, p orbitals look like dumbbells pointing along different axes, d orbitals take on more intricate clover shapes, and f orbitals are even more elaborate with multiple lobes. These shapes arise naturally when the Schrödinger equation is solved for electrons in atoms. They explain the multiple spectral lines, for example in hydrogen. They explain chemical bonding patterns, which will be elaborated in further videos. They explain periodic trends, such as the atomic size of an atom increasing down a group. And they explain everything that Bohr's model could not. So over here I have a diagram of the SPDF structure, and we can see that it isn't just a labeling system. Instead, it's a direct reflection of quantum mechanical behavior of electrons. It tells us that electrons fill orbitals of different shapes and orientations depending on which orbital they are in, each defined by a specific set of quantum numbers. And even though the Schrodinger model still requires that energies are quantized, like in Bohr's model, the underlying structure is more accurate and more consistent with details revealed by spectroscopy. To wrap up, we've seen how the simple picture of electrons orbiting like planets in Bohr's model wasn't enough to explain real experimental evidence like hydrogen's emission spectra. That mismatch pushed scientists towards a new understanding of the atom, one where electrons behave like waves and are described by probability instead of fixed path. This led us to the Schrodinger model, and from that, the idea of atomic orbitals. SPDF orbitals aren't physical paths, but mathematical regions where electrons are most likely to be found. They form the foundation of modern chemistry because they determine how atoms bond, how molecules form, and why elements behave the way they do. Thank you for watching.